Hello, this is the section 6.3 lesson on the topic of the method of least squares. Now section 6.3 is really just a continuation of section 6.2. So let's briefly review some of the highlights from section 6.2. In there we considered this random experiment of choosing a student and measuring his or her shoe length and their overall height. And in this random experiment, we said there were two random variables. Let x equal the shoe length and y equal the height. So three questions that we might ask about this experiment are: number one, how is height related to shoe length? Or stated another way, how is the random variable x related to the variable y? Number two, how strong is that relationship? And then number three, if we know a person's shoe length, can we predict his or her height? Or state another way, if we know a value of x, can we predict the corresponding value of y? Now in section 6.2, we answered these first two questions by going out and collecting some data. So here was the data that we had. We collected shoe length and height from 9 different students. So remember that these data come in pairs. Each student gives us two numbers, a shoe length and a height. And so to answer that first question with our data, we did a scatter plot. So we plotted the x values on the horizontal axis, the y values on the vertical axis. Each dot is a different student or different pair of data. And so we said that as shoe length increases, the height increases, and those dots kind of form a straight line that slope up from left to right. So the answer to our first question was that there was a positive linear correlation between x and y. Remember, correlation is just a fancy word that means relationship. Linear means that those dots form kind of a straight line, and positive means that that line has a positive slope. So now our second question was, how strong is the relationship? And so we gave a theoretical answer to that question with this correlation coefficient rho. That's also called the population correlation coefficient. But we said we're never going to be able to calculate that value exactly. So we're going to estimate it with this quantity r called the sample correlation coefficient. So three important points to remember about r is: number one, r is an approximation of rho. Rho is our population value. R is a value that comes from our sample. A sample statistic is an approximation of a population parameter. Number two, r measures the strength of a linear relationship. And then number three, the closer it is to -1 or +1, the stronger the linear relationship. And so if we've got a value close to 0, that means that there's no correlation or no relationship between those two variables. Okay. So for our shoe length data, we showed that the value of r was 0.974. And so our interpretation based off of that value and our graph is that there appears to be a strong positive linear correlation between shoe length and height. So then we gave a formal justification for that interpretation, but with a hypothesis test, where our hypotheses were that rho, the population correlation, equals 0, versus the alternative that rho is greater than 0. Informally, the null hypothesis is that there is no correlation in our population, and the alternative is that there is a positive linear correlation in our population. So when we did that hypothesis test, our p-value was very small, and so we rejected the null hypothesis and concluded that there does appear to be a positive linear correlation in the population. So we said that the practical significance of that conclusion is that we can use a straight line to predict height in terms of shoe length. And so that's what we're going to do here in section 6.3. We're going to talk about how we can make predictions. Okay. So going back to our third question, if we know a person's shoe length, can we predict his or her height? Or equivalently, if we know a value of x, can we predict the corresponding value of y? And so our goal in answering this question is that we want to find a simple formula for y in terms of x. And finding that simple formula is what's generically called regression. Now, before we start talking about how to do regression, let's give a couple of definitions here. So our variable x representing the shoe length is what we call the predictor variable, and y, the person's height, is called the response variable. X is called the predictor variable because we're going to use a value of x to predict a value of y. Or alternatively, we can think of y as a response to the value of x. So let's talk a little bit more about that final conclusion that there does appear to be a positive linear correlation between x and y. And let's ask ourselves, what does that really mean, that there's a positive linear correlation? Well, we're going to give kind of three different answers: an informal answer, a more theoretical answer, and then a little graphical interpretation of what that conclusion means. So informally, it means that the random variable y is approximately equal to mx plus b, where m and b are some constants that I don't know, and we'll try to estimate those using our data. So in a more theoretical term, instead of saying that y is approximately equal to mx plus b, we're going to say that y equals mx plus b plus some noise. Here, this letter epsilon is a random variable representing some sort of noise. Now, this epsilon is not the same epsilon that we used back in Calculus 1 when we talked about the definition of limits. It's just a symbol that we use to represent this random variable denoting noise. Okay. Now, graphically, what it means is that if we look at our scatter plot of our data, there is a straight line that quote-unquote fits the data. And I put fits in quotation marks here because what it means for a line to fit a data is maybe not well known or well stated. And so one of our goals here in this section is to define what it means for a straight line to fit a set of data. Okay. So we're going to think about this graphically, and that we're trying to find a straight line that fits our data. So that's the basic goal of regression graphically, is to find the slope and the y-intercept of the straight line that best fits the data. So let's talk about what that means. So here is kind of a simplified picture of what's going on here. So we've got a horizontal x-axis, a vertical y-axis, and we have three data points. x1, y1 we can think of as our first data point. xi, yi is like a generic data point, and then xn, yn is like our last data point. Now here's our line that's going to fit the data. These 3 points right here are not data points. Those are points on the line. We'll talk about those points here in a little bit. And this line has an equation that looks like this: y equal m hat x plus b hat. Now that equation is going to go by several different names. One name is it's the linear regression equation. Now we might ask ourselves, what's significant about the hats on these letters? Well, the m hat and the b hat are estimated values of m and b from our data. So remember, m was that slope from a couple of slides ago, and b is that y-intercept from a couple of slides ago. These are kind of like theoretical values. We don't know their exact theoretical values, so instead we're going to have to try to estimate them using our data. So m hat and b hat are the estimated values of m and b. Okay. Now let's talk about this point right here, which is on the line. And notice that the x-coordinate of this point is the same as the x-coordinate of this actual data point. Now this y-coordinate is different than this y-coordinate. This y-coordinate is on our straight line. And so we can calculate that y-coordinate very easily by simply plugging in this x-coordinate to our regression equation. So we plug in xi, that's this x-coordinate, to our regression equation. Take it times m hat, we add b hat, and the resulting value we're going to call yi hat. And this number yi hat is called the predicted value of yi. So it's the predicted value of this y-coordinate using our linear regression equation. Now notice that whenever we estimate something or predict something, we always put a hat on it. So whenever you see hat, think predicted or estimated values. Okay. Now next, so we could do that type of prediction for all of these different points. It's like this y-coordinate is the predicted value of this y-coordinate. This y-coordinate is the predicted value of that y-coordinate. So we're just talking about this in terms of a generic data point, but be aware that we could do that for any and all of our data points. Now, next thing we want to talk about is this vertical distance here represented by this dashed line. This vertical distance is just the difference between those two y-coordinates. So in kind of mathematical notation, this difference is the absolute value of the difference of this data, this y-coordinate from the data, and this predicted y value. And so we're going to call that the error in the prediction. Well, remember, our goal here is really to make predictions, and we want to make as good a predictions as possible. And so we want these errors to be as small as possible. And so that's really what we mean when we say best fit. What we want to do is find a slope and y-intercept of this line to make these errors as small as possible. So let's talk about how we could do that. How could we make those errors overall as small as possible? Well, one way to think about it is that we want to find our slope and our y-intercept that minimize our total error, where we just add up all those individual errors. So we just sum all this from 1 to n. And now yi hat was given by this formula right here. And so we want to try to make this total error as small as possible. Well, if we think about what's going on here, we're trying to minimize something. This sounds like a calculus problem. Well, how do we minimize something in calculus? Well, we take derivatives and set them equal to 0. Well, this expression here involves absolute values. Absolute values are hard to work with, especially when it comes to derivatives. So this idea seems reasonable, but it's not a real practical idea to work with. So let's state an alternate criteria. So again, we want to find m hat and b hat that minimize something. But now instead of taking absolute values, what we're going to do is square things. Now, why would we square things? Well, one thing that does is it makes everything positive. Now, it does more than just make it positive. But that it certainly does make things positive. Another reason that we square things is because squares are relatively easy to work with. A lot easier to work with than absolute values. And so what we're going to do is minimize. We're going to find m hat and b hat that minimize this total quantity right here, which is equivalent to this quantity right here. We just put in the formula for yi hat. And we're going to give that quantity a name. We're going to call it S. And that quantity S is called the sum of squares. You see why it's called the sum of squares, because it's the sum of the squares of a bunch of quantities. Okay? And so this right here is the criteria that we're going to use to find the slope and y-intercept of that line that best fits the data. So now, if you think about how do we do that? Well, take a step back and think about what's going on here. In this expression right here, yi, xi, these are all data values. Those are all given data values. Our only unknowns here are m hat and b hat. And so S here is really a function of two variables, m hat and b hat. And we want to make this function as small as possible. Well, from Calculus 3, the way to minimize a function of two variables is to take the derivatives of that function, the partial derivatives, with respect to each of those variables and set them equal to 0. And so that's what we're going to do here. We're going to take the partial derivative of s with respect to my first unknown m hat. And when we take that derivative, we get this, and we set it equal to 0. And then we take the derivative of s with respect to b hat, and we get this, and we set it equal to 0. Now, I'm not going to go through all these derivatives here, and you can read them from the book. One thing to note here is that don't let the fact that we're taking derivatives with respect to m hat or b hat scare you. The hats don't really mean things; they're just variables. in terms of thinking of this as a function. All right, so now we set each of those derivatives equal to 0. And so now our goal here is to find a formula for m hat and b hat. Those are only two unknowns. So we have two unknowns and two equations. We can, in principle, solve those for our two unknowns. And if we do that, we get this maybe somewhat complicated looking formula for m hat, and then this, this formula for b hat. So here y bar is the mean of our y values, and x bar is the mean of our x values. And so again, we're not going to go through the derivation of these formulas here in this lesson. The derivation is given in Appendix A6. So let's look at how we can use those formulas for m hat and b hat to calculate our regression equation. Okay? So here's our formula for m hat and for b hat. And here's our data, our shoe length and height data. And it's like in this quantity right here, we need to take each x value times its y value and then add them up. And that's what we've done here. Add them up, so this quantity is this right here. Next we need the sum of x, which is given right here. Then the sum of y, which is right here. Sum of x squareds. Here's our x squareds. We add them up. And then the sum of x quantity squared. And so we plug stuff into our formula right here. Do that arithmetic, and we get a slope of 3.878. B hat is y bar, which is the mean of the y values right here, and then minus m hat, which we just calculated, times x bar, the mean of our x values, which is right there. And so we do all that arithmetic, and we get our y-intercept of 25.84. So put it all together, here's our regression equation. Now if we graph that regression equation on top of our data, it looks like that. And we see that that line does indeed fit the data very well. Okay. Now a couple of quick definitions here, and then we'll talk about how to calculate these on our calculator in a little bit. This equation goes by several different names. It's called the regression equation. It's also called the least squares regression equation. It's called the least squares because we minimized a function involving squares. It's also called the best fit regression equation. So now we've calculated our regression equation. What can we do with it? Well, as a simple example, let's look at this scenario. So suppose a crime scene investigator finds a shoe print outside a window that measures 11.25 inches. And would like to estimate the height of the person who made the print. Well, we can use that regression equation to make predictions, right? That was our whole goal. And so there's our regression equation that we just calculated. And what we're given in our problem is really a value of x, 11.25. And so we're going to plug in x equal 11.25 to the regression equation. We do that arithmetic, and we get 69.47. So that number, 69.5 inches, is called the best predicted height of the person based on the data. And we do need to add this qualifier based on the data, because if we had a different sample of students, we would get a different regression equation and we get a different predicted height. So it doesn't mean that the person is going to be exactly 65.5 inches tall. It's just a one number estimate or one number prediction of the height of that person. Okay, so regression equations are relatively easy to calculate because the calculator is going to do all the work. We'll show how to do that here in a minute. And they're also very easy to use. They just involve plugging numbers into the equation, do some simple arithmetic, and we're all done. However, we have to caution against overusing regression equations. So first caution here is that if there is no linear correlation in the population, then do not use a linear regression equation to make predictions. So specifically, if we do our hypothesis test and we do not reject the null hypothesis that rho equals 0, then that means there is no linear correlation in the population, so we should not use a linear regression equation to make predictions. So how could we make predictions? Well, in this case, the best predicted value of y is y bar, the mean of the y values. and that's our best predicted value regardless of the value of x. Now I won't go into the reasoning of that here in this lesson. So if you look at example 632, we talk a little bit more about that. The second caution is to only use the regression equation to make predictions within the range of the x values of the data. So as an example of what we mean by that, let's suppose that another investigator measures a shoe print of 8 inches. And so let's try to predict the height of our person. So here's our data. Notice that our shoe length data goes from 9 up to 13. And here's a graph of that. We see that over that range from 9 to 13 we get a nice straight line. However, notice that 8 is outside of that range. Now, we could certainly plug in 8 to our regression equation. Take the slope times 8 plus that, and we get 56.86. That's easy to do. However, that prediction may or may not be reasonable. And it's because we don't know the trend of our data for x less than 9, nor do we know the trend for x greater than 13. Right? This trend may continue. The straight line trend may continue. Maybe it drops off sharply. Maybe it levels off a little bit. I don't know. I just don't know what the trend of the data is for x less than 9. And so this calculation here was easy to do, but it's not appropriate in this case because we don't know the trend of that data. Okay, so lastly, let's talk about how to calculate a regression equation on the calculator. And really, we've already did it back in section 6.2. So the first step here is to enter the data into lists L1 and L2. We'll put the x values in L1, the y values in L2, which is exactly the same as we did in section 6.2. Next, we're going to go to the linreg t-test command, which is exactly the same as what we did in section 6.2. Now, our window here looks like this. We put our x list L1 here, our y list L2, and then we put the form of our alternative hypothesis in here. Now, if all we want is the regression equation, it doesn't matter what we put for our alternative hypothesis, because that's not used in calculating the regression equation. However, in this row, the calculator wants to know where do we want to store that regression equation. Now, the default here may be y1 or it may be blank. In order to select a y1 there for the regression equation, go to hit the vars key, and then go to, you just get a window that looks like this. Go to the yvars submenu, choose option 1 function, and then you'll get a list of the different y functions that we can select. We'll just select the first one, y1. So if you do that, that'll paste a y1 there for the regression equation, and that means it's going to store the regression equation as the y1 function. Okay. Then you hit calculate, and you should get a window that looks like this. So again, the top row says we did the linreg t-test. The second row gives the form of the regression equation that the calculator uses. Now it calls it y equal a plus bx. So a is the y-intercept and b is the slope. I don't know why the calculator chose to use those letters to represent the slope and y-intercept, but it really doesn't matter as long as we understand what's going on. So at the bottom of this window, we have a equals 25.8. That's our y-intercept. Now if we scroll down a little bit more, we see right here b equals 3.878. There's our slope. These other quantities we talked about in section 6.2. Now one other quantity here is s. This quantity is called the standard error. The standard error is an estimate of the standard deviation of that noise that we talked about earlier. Now, for purposes of section 6.3, that's not terribly useful. Section 6.4, we do talk about how that standard error is used. But for regression purposes, the most important results here are the y-intercept a and the slope b. Now, real quick, let's look at some other outputs from our calculator. If we go to the y equals menu, we'll see here at y1 it has stored that regression equation there. Now it's given us many more decimal places than what's really necessary, but that's okay. Now we can graph that regression equation on top of our data. And so the first thing we need to do is set up our statistical plot. So if you hit the second and then the y equal key, that'll get us to the stat plot editor. And we'll choose one of these plots to set up. I'll choose plot 1 there. We want to make sure plot 1 is turned on. We're going to choose the first type for our scatter plot. Choose our X list and our Y list, and then whatever mark you want. And then we need to go zoom 9 for zoom stat. This is always the step that I always forget. So make sure you go zoom stat. And when you do that, you should get a window that looks like this. So here's our scatter plot, and here's our regression equation plotted right on top of the data. Looks like it's a good fit. So that's all there is to calculating the regression equation and graphing it on top of our data.